Okay, now everyone online should also be able to hear me. Great. So let's start. Let's get going here. Wow. Cool. So what will we do? As always, we'll do some admin. We'll review the second set of notebooks. I know you all want to talk about the compute graph. We'll go through questions and answers. And then we'll talk a little bit about deep learning as a field. And Hendrik Strobold did in according to me asking him, a very cool visualization that's now also at Neuroscience and very popular. And we will basically give you the gestalt of the entire field. Everything that happens in the last 60 years of deep learning will be in a way in it. So let's get going. The first thing that I want to encourage you, and my co-teachers don't even know about it, but I think it's a fun thing to do. As you know, all our tutorials on GitHub, they aren't perfect, not like everything, like life. Not like we make mistakes in the tutorials. They aren't as good as we'd like them to be at times. I want to encourage all of you, if you see things that are unclear or things that are just not good or things where you feel, oh, I have a better description of that, put in a pull request on GitHub. And I will make sure to give extra points to people who put pull requests in, because I think it's a cool way, and it's a way of getting used to this modern way of collaborating on teaching and collaborating on code and all those things. Permits. By now, everyone should for real have their permits. Is anyone in here who still doesn't have a permit? Okay, wonderful. That's what I was hoping to hear. It's just like admin sometimes goes wrong, and so it's important to ask. At discussion, so UPenn is moving off of Piazza, it seems. And so this year they are using At Discussion. At Discussion is basically a clone of Piazza. And we will be posting you the sign-up link as soon as possible. Like tomorrow. Wonderful, cool. Let's talk a little bit about this week's notebooks. So there was one exercise which led to a lot of confusion, and I apologize for that. So here's the compute graph. How to interpret this compute graph? Now, if we just have multiplication, we have basically B is A times W1, C is A times W2, D is W3 times B plus W4 times C, and L is defined on terms of D. The confusion that arose is because we have 3x3 matrices. 3x3 matrices are in lots of ways a bad idea for an exercise, because there's multiple ways how we can interpret things. Now, specifically, there's two ways how I can multiply A, which is a 3x3 matrix, with W1, which is also a 3x3 matrix. What the exercise meant to ask you to do is do scalar products, but you can obviously do a matrix products. We didn't specify the loss function either. We meant mean squared error versus like a 3x3 matrix that all contains the same value that is drawn according to how we set it. In that sense, obviously, however you solve that problem, as long as you solve it in one of the possible ways, you will deserve full points, and it's a correct solution. Okay, now, what you saw in the tutorial is also the power of compute graphs. Why are compute graphs so awesome? It's very easy for PyTorch to build this compute graph while we do our forward computation. Why? Like if I multiply two things, it just needs to do bookkeeping and kind of say, yeah, Conrad just multiplied these two things. Specifically, Conrad just multiplied with A with W2 and called the result C. As long as we have that, we can basically build that compute graph on the fly. At early times, PyTorch was doing that. TensorFlow wasn't doing it quite like this. And that's why when PyTorch started winning out big time against TensorFlow. By now, TensorFlow has a similar functionality, and people often use TensorFlow to say solve things that you need to compute on edge devices or something like that, where Google support, as far as I know, is much better. Okay, so but as we can compute this, produce this compute graph on the forward path, we can automatically propagate it back, because like once we have that compute graph, back propagation is really just taking every arrow going in the other direction. What's the implication of that? How much slower is it to calculate the gradients for your typical network as it is to calculate the loss? Okay, why don't I choose a random person here? Everyone's looking away. What about you?
Calculating for each node in the graph going forward, and what you would have the same amount of edges going backwards. So I think you would also the edges denote multiplication going forward, and then the chain rule is multiplication. So
yes, you're exactly right. Perfect answer. What's your name?
Will.
Will, thanks so much. And if I ask you questions, if you could just say your name, like I'm Conrad, and my answer is, that would be awesome. But thank you, exactly right. What we have when we calculate on the forward path, what's happening on that arrow, or what's happening when we multiply that, which is most of the time a neural network spends doing big matrix multiplication. We multiply with a matrix. What happens on the way back? Well, we multiply with a transpose of that matrix. So it's really exactly the same operation. And that's why generally the forward pass takes about the same amount as the backward pass. It's not exactly the same amount of time. So it might be factor 3 slower because of some optimization stuff. But the rule of thumb is that going forward, and someone needs to mute themselves, going forward takes exactly the same amount of time as it comes going back. What that means in practice is that having the gradient costs you effectively nothing, costs you a factor of 2. And of course, as we know from the previous courses you took, we are much faster optimizing if we have the gradients. Okay, so this was the first part. We then moved on to see some linear regression. Now, linear regression, we don't do that because linear regression is interesting per se. I mean, in lots of ways it is interesting. But the reason why we were talking about linear regression is the domain in which we can have really strong intuitions. Now, like we can calculate all relevant gradients mathematically, just it's a product of matrices or their inverses. We know what the right solutions, how they look like. We can decouple networks and make them independent. And that's kind of what gives rise to the race models later. And even if you have a nonlinear neural network, locally, it will operate like a linear neural network within small vicinities of points. So if we want to have an intuition of how or why neural networks work, linear learning is the right place to look at, because that's the only place where we really have strong intuitions. And that's why we start the course with linear networks. And for these linear networks, we can have all these proofs. We can say linear networks converge exactly in this way, or linear networks will have exactly these kinds of dynamics because we can analytically solve it for it. And otherwise, I think so. There's also evidence that in a lot of cases, now if you're in very high dimensional spaces, you don't generally even need overly nonlinear functions. Sometimes you don't need them at all. And in fact, if you look at, say, the work of Ben Recht, one of the things that we often learn from him is that if we do linear regression just really cleverly, we can often solve problems at almost state-of-the-art levels, sometimes at state-of-the-art levels. So in that sense, like linear regression gets a bad rap. In high-dimensional spaces, linear regression can do a lot for us. Now, we also saw how we can use singular value decomposition to convert a linear neural network, as we have it to the left, multi-levels, linear neural networks doing stuff, and how we can do singular value decomposition to basically convert that network into a different network that is just linear. No? So that is the mathematical transformation that makes the Sachs paper possible. And that in a way links what we did in the tutorial with the underlying theory that basically if we have a multi-layer neural network, we can do SVD, which makes it into one matrix. And as such, then all the gradients are exactly the same in that SVD space. So we can convert a network into a set of parallel networks that evolve independently. And this set of independently evolving neural networks that are all just linear and deep is ultimately what gives rise to these typical race dynamics type results, where we see the different components kick in at different points of time. And that's why often learning curves look like that. Now, what you might naively expect at first is if I have a linear network, I have linear dynamics. Things should basically exponentially get there. Now, like I start at 0, it goes up. So why does it exponentially rise? As soon as I learned a little bit, the relevant activities went up. Because the activities went up, I go faster, namely by the fact of activities that are already accumulated. And therefore, the dynamics is exponential. But what we often see in neural networks, and also in these big linear neural networks, is that instead we have these functions that like do these little steps. So why is that happening? Why do we have that the steps kick in one after the other? So who has an intuition? It's the most normal thing when you train neural networks. They go, nothing gets better, and then it gets quite a bit better, and then nothing happens for a while, and then again it gets quite a bit better. Anyone who ever trains a neural network has seen that. Why is that coming? Where's that coming from? Yes?
It could be very different layers, like first the way to get on the first layer, then on the second layer, like it takes a while for the way on the first layer to change what the way the second layer is changed.
That was how I originally thought about it. But let's think about this. There is an equivalency between those two networks. It's exactly the same network. It's just to get from this network on the left to the network on the right, we do a transformation, in a linear transformation. So if we have this kind of a structure, know that only at the input layer, they basically see different projections on the input. But otherwise, they're independent of one another. So if we have this, it will exponentially learn. Like it will be close to 0 for a long time, and then it will go up. And then, of course, at the end, it converges. Each of these picks up on a different thing. Say, the first dimension could say, pick up on the first principal component. The second one could pick up on the second principal component or something. So what we have is the first one learns exponentially, and until it's as good as it can be. At that point of time, it's converged, but the second one might still be very small, very, very weak. It's still in this exponential phase. Mind you, we initialize neural networks close to 0, and there's a reason why we do that. The reason why we do that is exactly to enable these kinds of dynamics that we start at low levels, and then like they kick in one after the other. And that ultimately means that the first component is what you see in big blue here on the left-hand side, that one here. Jumps up, exponentially solved. But the second component is still so weak, barely visible in the weight matrix, that it doesn't make you any better at it yet. But it grows exponentially. And then at some point of time, it kicks in and it gets this step down. And so on and so forth, component by component. And this is something, the cool thing about it is that this is analytically solvable. This is, you can just solve it with math. Yes, Anka.
asking why these networks are.
So why are the two networks equivalent? Let's go back here. If everything is linear, and I don't have here the, yeah, no, like if everything is linear, then we have one matrix basically here. We have another matrix that's here. We have another matrix that's here, and another matrix that's here. What does the overall network do? Now, what does it do? I have a multi-layer linear network where every layer is characterized by a linear matrix. What does the overall network do? It does what? Well, maybe it's a classification, maybe it's something else. But the important thing is, if I have a multi-layer linear network, it is a single layer neural network. Now, like I have the network is a product of matrices. Now, when I have a multi-layer neural network that is all linear, I have Y, the output, is W1X. That's the output of the first layer, times W2 times W3 all the way up to Wn. Okay, so the whole network that I have on the left-hand side can therefore be rewritten as just, no, I can take all these and bracket like that and say V times X. Therefore, this is just a matrix multiplication. Now, this matrix V, I can, of course, do singular value decomposition of that matrix. Okay, therefore, I can basically do a coordinate transformation of X so that otherwise, this is just a linear network. Now, like I can write it as basically an input rotation matrix followed by a scaling on every dimension. Now, the scaling on every dimension basically starts at 0, and it has those dynamics of being multiple linear levels that are just all like multiplying with small numbers. And all those numbers go up, and that's where the exponential dynamics come from. Great question. And how do I mouse draw? Mouse. Good. Oh no, now I can't. How do I? Oh, annotate. Clear. What? I said clear, clear all those. Okay, much better. Yes, it's hard to, in any case, there's the learning dynamics. Ah, wonderful. Okay, so if we would just have one layer here, then we would have the dynamics that we should expect for such a linear system, that it just exponentially goes down there. If we have dynamics that are like that, it kind of goes in steps. Now, let's be clear where the difference is. With that, I just argued the two of them are identical. But with what I have there, I just said, well, it's exponential. Like, but if this is just linear, why would it be exponential like that? Here's why. I have a small, when I do an upgrade step, I do a small step, but I do it on the first layer, and a small step on the second layer, a small step on the third layer, and so on and so forth. Therefore, any small step that I make kind of gets amplified as I go through it level by level. And that's where the exponential dynamics comes from. So you can say what we do for this step, where we make it into independent dimensions, is that we basically take these deep linear networks to characterize the learning dynamics, but we take the rotation to characterize what maps on which dimension. cool. So Matthew asked, does each network have one gradient and you just progressively go down at each iteration? No, each layer is learned at the same time. Now, like that's how we train neural network. We do gradient calculation, last layer, previous layer, previous layer, previous layer, previous layer, beginning gives me the gradient vector. I go a step into that direction, and that's it. And then Hong asks, is there a particular meaning for the neurons being white or dark? No, this is just to like understand how things look like here. Sai asks, can you explain each component learns a different thing? That part is confusing. In the linear thing, it's assumed that we have a projection that happens at the first layer. In any case, for anyone interested in the deeper part, read the Sachs and so forth and Ganguly paper. But there was for sure an exercise that did exactly this. Good. Let's talk a little about, yes. When I say what? A component. It depends a little. I don't know which sentence of mine. Oh, yes. Yeah, in this case, each of these steps where it jumps down is really where one of the parallel neural networks converges. You can say every one of these many parallel neural networks has a dynamics that looks like this. It's just that, not like, in fact, let me draw it the other way. It kicks in like this, but some of them basically kick in like this because they're close to zero. Some of them kick in like this. Basically, the ones associated with large singular values kick in at early periods of time, and the ones associated with small ones kick in at late components generally. So the tutorials also spoke a little about cost function engineering. Yes?
Why is it that singular values that are higher kick in earlier and singular values that are lower kick in later?
Yeah.
Is there a reason?
Is there a reason? Yes. So the singular values that are large, and when I say singular values are large in the inputs, the singular values that are large basically produce large gradients. Now, so basically, if I take a component, if I take a vector in the input and I scale it to make all the vectors say twice as big, it means that learning at all layers happens twice as fast. And because learning at all layers happens twice as fast and we're in a deep network, it learns exponentially faster. That's why the size of the singular value ultimately translates to the speed with which it learns.
When you go from the Force-connected graph to the linear one, are we multiplying by the singular value decomposition? Or are we like multiplying that network by the singular value decomposition?
So what really happens here in the analogous graph here?
Conrad, can you repeat the question?
So yes, great question. So the question is, where do we see the singular values in a way in this graph? So what happens here is that on the leftmost linear chain here, we have that that basically the input has high variance. On the second one, the input has less variance. On the third one, the input has less variance. That's when we do singular value decomposition. This is how they are ordered. And the ones that have high variance, basically, therefore, see strong correlations of, or like strong gradients, because each weight helps you more by increasing it. And therefore, because every weight sees that, we have exponential speed differences. Great question, but like, yes, so let's see. Yeah, Lyle is answering some of them online here. So that's the learning dynamics. So, but the important thing is the kind of learning that we see. So let's zoom out from all that. No? The way of thinking linearly about learning in these systems explains why they have these long periods of time where very little happens, and then periods of time where something happens. That's true for the nonlinear one, for the linear ones. It's also true for the nonlinear ones. And we can gain insights into why this is happening by thinking about it like that. So real-world learning curves very much look like what we have down there, which seems bizarre if you realize that this is just linear learning. But still, it happens like this because the spectrum of the singular values looks like this. So let's talk a little bit about cost function engineering. What we use there is the mean squared error at first. Now, like that's the standard cost function. Why do we usually use mean squared error? Let's give someone else the chance. Why do we use mean squared error? Yes?
Minimize the mean.
Minimize what?
Yeah, to minimize the mean of the
yes, it minimizes the mean of the error as well. But why of all cost functions is mean squared error specific? Yes. It does what? The mean squared error, it's relatively intolerant to outliers. That is one of the problems. That's why why we sometimes use mean absolute errors. But why do people use mean squared errors? Or why in statistics do we use mean squared error techniques? Yes.
Because the difference gets amplified.
Okay.
Between the outlier and the figured line. So,
yes, it does. But what's special about mean squared error estimators? It is convex, as is the mean absolute error. Yes. It is differentiable, exactly. Everything that we use needs to be differentiable. But also when it comes to statistics, it's the one that gives you the best power. Why? Because it ends up, if you minimize mean squared error, imagine you're one-dimensional. It means that you weigh every data point proportional to what it is. Okay, so this is the one, mean squared error leads to estimators that have the strongest statistical power, provided that they're drawn from a Gaussian distribution. Now, like if they're drawn from a distribution with outliers, then all bets off. So why would we want to use the mean absolute error relative to the mean squared error? Let's give people a little of a chance here. Mean absolute error. No, like why are you using it? Yes. That's right. Yeah, the mean squared error means that a data point that is 2 times as far away has twice the importance in a way. The mean absolute error gives every data point the same importance. The great thing about giving every data point the same importance, now you can say it's basically just a vote. Do I want it up or do I want it down? Everyone has the same vote in that system. In the mean squared error, the further away you are, the more of a vote you have. But like that, of course, means that those outliers that are factor 10 to the 6 further out have 10 to the 6 the influence. So we use mean absolute error if we believe that we have outlier in our data set. And sometimes we use number of corrected guesses. Now, what I want you to, if you will solve real world machine learning problems in the real world, what's the objective function that you should use? Now, imagine you're in a company. They say, give us a price estimate. Or like, give us an estimate of how much items we'll have in the market. Give us an estimate of how many customers we'd have if we would try and do an advertisement campaign. Those are the questions that the real world asks us to answer. What's the right answer to those? What's the cost function? Yes. Oh, but if there's outliers in real life, imagine we talk about pricing of goods. I'm going to sell you little presents. You say you pay $10, you say you pay $8, you say you pay $11. That gentleman in the back left corner says 10,000. I should have asked for $9,000 for this because he would have bought it. So in that sense, it's not that simple. Mean absolute error is not what we want to optimize. Yes. Try both and see what matters. That's something that we can do. But this serves as an important reminder for all of you that the way that you don't think about cost functions. Now, you will have seen cost functions in 519, 520. You will have seen cost functions all over the place. The right answer is whatever the world needs you to optimize for. So let's say I talk about advertisement campaigns. It's about how many dollars I will make. Now, if I advertise, there's a certain risk on both sides, and maybe like there's outliers of how much people are willing to pay. I don't care. In that case, I want to maximize the amount of money that I make. If I'm a company that wants to like not have to deal with like returns of products because they are broken, I don't want the mean squared error. I want to have the probability that I need to reimburse that money times the number of people that buy it, minus the cost that it costs me to build it better. So in general, the cost function you want to optimize is the thing that matters in the world. And this is something that I often see data scientists ignore, and it's a real problem. And ask yourself, what is the real cost function there? There is not one that is better. The one that is best is the one that describes the real problem in the real world. So if you want to win a Kaggle competition, who has participated in Kaggle competitions? So how did it go?
I'm doing one right now, and it's going okay.
Okay, so if you want to do well in a Kaggle competition, there's usually a definition of which function scores the winning thing. So for example, they might say, your score is how many you correctly predicted. They don't care about mean squared error. The ultimate cost function is how many you correctly predicted. What you would normally do in that case, you might optimize the log probability of the data or something because that has better statistical power, mean squared error because it has good statistical power. But what you ultimately get paid for is how many you get right. What we do in those procedures is almost always we train the machine learning system and then we train it again at the end to get the right cost function. Okay, so I want you to keep that in mind. The cost function is what matters. And you can massively do better in most real-world scenarios by thinking hard what the right cost function is. Now, you also heard a little bit about the intricacies of network initialization. Why does it matter? Exploding gradients, you have trouble. Vanishing gradients, you have trouble. So you saw Xavier and he, but importantly, you also saw the principles that are behind it, with which you can derive the optimal ideas here in all cases. Now, we have time for that. I want to make sure that you all have the right intuitions for high-dimensional data. So we are drawing data from an n-dimensional and anchor. I have to remove the chat so that everyone can see. So if there's any questions, please ping me. We draw data from an n-dimensional isotropic Gaussian. Gaussian n 0, sigma on every dimension. Now, every dimension we draw independently, so there's no joint, no correlations. And n is big. Now, the reason why I talk about it is the number of weights in your neural network is large. All the intuitions that you have from low dimensional spaces when it comes to neural networks is entirely wrong. The vectors are often large. The matrix, the weight matrix or the weight vector is definitely large. So we really need those estimates, the intuition for high dimensional spaces there. So I draw two vectors in that space. What's the distribution of angles between them? No, like this. 90 degrees. Yes, why? That's right. The dot product will always converge to 0. We have so the dot product between any pair of vectors goes to 0 if they're randomly drawn. Why? Every dimension is drawn independently from each other. So therefore, the variance goes down as 1 over n, where n is the number of dimensions. Therefore, the expected value of the scalar product goes down. And the ratio of the scalar product between them relative to their lengths goes down towards 0. So in high dimensional spaces, every pair of vectors is orthogonal to one another. Now, in neural networks, why does that matter? Let me ask you a completely different question. I show 2 stimuli to a neural network. One thing, this is a cat. Another thing, that's a dog. I get some gradient. When I make a mistake on the cat, I get a different gradient when I make a mistake on the cat. I learn the dog first. I do my little gradient step. Is that cat that I'm gonna learn after the dog gonna interfere with the dog? How much? Well, we just had it on the thing. Now, like the angle between any 2 vectors is 0. Apply this to this problem. I have a cat. Now, and imagine that the cat is independent of the dog. They're just 2 completely random white noise stimuli. I know cats and dogs share things. Let's ignore that for the moment. The cat, random vector, and I do gradient step on the cat. How much does that change what we have from the dog? Okay, it doesn't change it at all. And this is very important. And this is, without that intuition, you can never understand neural networks. Why? What's happening? I calculate the gradient after the dog, which is a vector in a space of the dimensionality of the length of the weight vector. Not like the gradient is as long as the weight vector. Okay, I have 1 vector there. How much does my representation of the dog change? Well, it's the weight vector of the dog multiplied with the gradient vector of the cat. That's how much learning the cat changes the dog. And I cannot, you've got to relay any message. I don't see anything.
Okay, why is actually saying that it's not followed?
Okay. I show you a cat. You're wrong about that cat. You say, this is a crocodile. Gives me a gradient vector. Not like, let's write it out so that, okay, here. The cat gives me a gradient vector. The loss of the weight. Let's call it 1. Okay, then what I do is I have a weight vector, W, and this one is going to be transformed as W plus W minus epsilon dl over d, let's see, here, eta. Okay, this is gradient descent. Now, I have the dog. So I first have this, then I do this, and I have the dog. Now, imagine before showing the cat, I totally get the dog right. Yes? Oh, okay. Good. For the next one, what we have is we have a vector that is the gradient at the time where I showed the cat. So not like scenario, I have a network, it works just fine for the dog. I have a weight change that is proportional to the gradient following the cat, the mistake on the cat, and then I go back to the dog. What I have is I have a new I have a new weight vector, and I have a projection, if you want, that deals with the dark. So now I have two weight vectors, the original one and the new one. And I have a projection of that, say, that is the readout that tells me about the dark. Those two vectors lie in a very high dimensional space. They will, on average, be orthogonal to one another. In fact, as we go towards high dimensional spaces, they're orthogonal. They're essentially orthogonal with probability 1, which means that learning one thing has only a weak influence on learning other things in neural networks. And that is the key to being able to learn anything. Like the vector that I have in any weight, in any layer, sure, if I learn something, that vector will be a little different. But on average, this will be orthogonal. And in high dimensional, as I make our layers wide, I will be arbitrarily close to being orthogonal. So in the limit where our network is arbitrarily large, the network, the change that I do in terms of one thing, if they are random input vectors, will have vanishing influence on anything else. Okay, so that's the first one. The angle is always 90 degrees, which means that things that we store or change in neural networks will generally have weak influences on one another. So what proportion of their mass is within a delta thickness of the distribution? Now, like what we have is if we do it in 2 dimensions, we're gonna have a Gaussian in 2 dimensions. In 1 dimension, it looks like this. In 2 dimensions, you can say here, I have my Gaussian. Here, and then we can say which proportion. Now, if I look at the density as a function of distance, in this case, it looks like this. In 1 dimension, it looks like that. In 2 dimensions, it looks like this. Now, like in the beginning, the size of this ring goes linearly up. So we have linear times the Gaussian looking a little bit like this if I go into 2 dimensions. So there's an area where I have most density. Which proportion of the density of the high dimensional Gaussian is within a small delta around the highest point? In other words, what's the typical distance between vectors in a high dimensional space? Okay, all of them. They basically, any pair of high dimensional vectors is at the same distance of one another. Again, why does it matter for neural networks? It kind of means that there's nothing, that any 2 things that I learn in a way have the same distance from one another. In low dimensional spaces, that is much less the case. Now, all the things that I told you, like are before a network picks up structure. The network might find out that everything actually really happens in a 2-dimensional space or something, in which case that intuition that we can have about high dimensional spaces really changes. But the important thing is that in many cases, we can have intuition there. And say the neural tangent kernels is a way of using that intuition to really derive how neural networks are a bit like tangent support vector machines. Great. Now, let's jump to questions and answers. Who has any questions for today? I can pull them out right now. Okay. Can we go over the compute graph? We already did. The slides link, yes, I'll share them. Can we go over how float 32 numbers introduces a nonlinearity in deep neural networks? Great question. If you store a number, then in a way, the way we store them is that we have a bit that defines the sign, positive or negative. And then we have a set of values that define the exponent. And then we have a set that defines the values. Now, so let's ignore sign. Like it's going to look the same, negative and positive. But let's, the exponent will have a certain maximal value. Not like we only have so many bits. And do I know by heart now if how many of them the float 32 has for each of these? No, I don't. But you get the idea. Like that we'll have like, what do I know, 10 bits that say how big the exponent is. So 2 to the 10 is then the largest number that we could have here. And then here we have the values. Now let's take the smallest value that this can describe. The smallest value that this can describe is basically times 0. Okay, so, and then the values can therefore, at that smallest value of the exponent, be like 1 or 2 or 3 or 4. What that means is that we will have something, if we zoom in all the way, we will have 0. And we will have 0 up to a certain level. Namely, it will only become 1 once it's above a certain value, because then here, if you want, we have the threshold value where we want to go to what's 1. So what we have is we basically have that then it's going to be 0 up to some level, and then it's going to be 1 and 2 and 3 and so forth, and it goes up linearly. The same thing happens on the negative side. So in the vicinity of 0, we have a region that is exactly 0. That is a nonlinearity. Now, like if I have 0.49, it's still 0. And then if I have 0.5, it's 0.5, it's 1 here. And then if I have 1.5, it's 1, and so on and so forth. So the way it's implemented is that there's this region where it's exactly 0. And that region where it's exactly 0 is basically the nonlinearity that allows us to learn the XOR. And the reason why we have this XOR thing in our deck is just as a reminder, your system isn't, the implementation of the math that we have isn't faithful to the math. So if you have an exponential function, it goes to infinity at some level, at a very small level, like e to the, what do you know, 30, or like e to the 100 is suddenly infinity for float 32. And so we are in this domain where in all kinds of ways our neural network can push us out of the domain where our abstraction is correct. And this like nonlinearity at 0 is just one of the ways how this can be wrong. Wait, let me make sure I can see those. Cool. What other questions do we have? Yes.
Isn't mean absolute value, like taking the absolute value of a function, not differentiable? I was trying to say that like mean squared error and absolute error are different in that way.
Yeah, this is a great question. Isn't it that absolute error is not differentiable? And the answer to that, it depends on how often it's differentiable and in which places. So if we have the absolute value function, now you can say there exists one place where the derivative is undefined, here. Everywhere else it's defined. The probability that we'd ever hit this value in the general case should be 0. Like if I have bias and so forth. So you can say that ReLU is in practice always. The derivative is defined. Now this is ReLU for the ABS value, exactly the same thing. Now the second derivative of this is much more problematic. Now, like the second derivative is 0 everywhere apart from that one place where it's infinity. And then, so for things like ABS or ReLU, we can't really use methods that want to use the second derivative. And there are a lot of techniques where having the second derivative is very useful. For example, when you do meta-learning, where you want to say, improve the learner that improves the behavior of the animal. Then we have a gradient in the learner, and then we have a gradient in the meta-learner after the ln, and in this case, we need stuff that is twice differentiable. But like ABS, well, is differentiable everywhere apart from one place. And of course, the derivative looks like this, where it's positive and negative. This is how the derivative of the absolute value looks like. And there you can see where that voting strategy comes from. Everything that's on the right-hand side contributes a fixed value positive to the gradient. Everything to the left contributes a fixed negative value to the gradient. Any other questions? Yes.
What you were saying about learning as an does that only apply if the network?
Okay. it's very complicated to talk about these things. The question is, what happens if the network is nonlinear? Now, like, it turns out that in a way, locally, if I do a very small change, that change is always linear. Because if I have, for example, if I have a multi-layer ReLU network, then at higher levels, I have linear surfaces. And so everything is linear. And if I have something that, say, uses smooth functions, then as long as I make my epsilon really small, everything is linear. But you're absolutely right. No, like if I allow big changes, then a lot of these intuitions go down the drain. And arguably, this is one of the reasons why we do gradient descent learning with very small steps. You know, like we did extensive testing if small steps are better or big steps. And it turns out that doing steps where basically the real change makes relatively small changes to the input-output function is the domain in which things work well. And there's deep mathematical reasons. So for everyone here who's interested in the mathematical aspects of, or the theoretical aspects of deep learning, this is a wonderful field where there's so much that we're learning at the moment and so much that we didn't know until very recently. Is the professor muted? Yes, the professor was muted. The long one. In week 2, day 2, we saw that the absolute value of weights increased to convergence point, but this should not always be the case, right? Since we're initializing weight close to 0 after backpropagation, the weights can reduce further to reach convergence point 2. Yes, there's nothing fundamental that says that a given weight cannot go down. But if we initialize it at 0 and we think about it from this linearization of the overall problem, we have these independent things that come in one after the other. So for those, they will often have that property. But otherwise, like, sure, there's no doubt that we can construct cases where some weights will ultimately go up and then they will go down in a way that, like, ultimately, in the end, is not the lowest value. It's probably the case that for certain scenarios, like everything drawn from Gaussians or something, you can prove that it will always, in the limit of large n, have that property. But there's nothing that ultimately says this can't be the case. It's just that in practice, we initialize close to 0. If we initialize to very large values, then neural networks have very different properties. Okay, UC Shao says, can we talk about why we have exponential growth period of learning? Why is it important? The reason why it's important is because it gives rise to real-world training phenomena with deep learning. Now, like, we see that oftentimes nothing happens for a long time, and then we learn something very quickly. What's happening? What's happening is in that long period where it looked like we weren't learning something, we actually did learn something, in fact, exponentially. It's just that if you start something very close to 0, it can even exponentially take a long time until it gets to be visible. And so in that sense, it gives real-world explanations for that. And why do we have it? Again, like, because like we do the weight update at every level along the hierarchy. Great, so let's get to the highlight of what I really wanted to do with you. Yeah. How do I get? Yeah. So, oh no, I just closed. That's not very good. What? But like now it closed. Okay, here. Oh, come on. Okay, my computer is basically dead. Hmm. Okay, a few extra clicks. And there we go. Okay, I'm just totally baffled what is making my computer so slow. I did plug in a few of the USB things here. Good. Now, this is all of the heavily cited Nlp papers over 60 years. Everything that you will learn during this course has at least a few papers about it. So this is the gestalt of the space that you're entering. And I want to give you an idea of what that gestalt is. Now, what are the main parts of the course? We will have a section on reinforcement learning. We'll have a section on computer vision. We'll have a section of natural language processing. And because I'm teaching it, there's a little bit of neural network, a little bit of actual neurons going to be in it. So this is all the papers in 60 years clustered so that we can meaningfully see what these areas are. So let's look at the oldest pieces here. You see this cluster here? It's mostly old. What's going on here? Let's look at that. What do we have here? So here we have a cluster. What you see in the quick summary here is image vision, computer using recognition, visual recognition, and so forth. So a lot of these papers are old school computer vision papers. Not like here, a combined corner and edge detector, 1988. It's basically old school computer vision, an iterative image registration technique with an application to stereo vision. It's cool. No? If I want to see how fast something is, I need to take what my right eye sees, what my left eye sees, make sure that I can see how they align. And it's a little bit difficult because it's not going to be quite the same image. And so we have those techniques for that. Here, versatile camera calibration technique. So this is one of the areas where this broader field that you're in started. People were basically like, vision, isn't it magnificent? Let's see what we can say about vision. And they went to the conference called Neuroscience, and they presented their papers there. And some of them were inspired by neuroscience. Some of them were just inspired by making stuff work here. boosted cascade of simple features. Just says I take a cascade and then I run boosting. So this is like relatively old school machine learning applied to basically vision data. Jitendra Malik here is a big person in that area. Here, one of the newer paper, rapid object detection, is being used by quite a few people. Here you see eigen features of images. They took lots of photographs, ran principal component analysis, and said, these are the important dimensions here. This is what that cluster is. You will hear absolutely nothing from me about that cluster after today. Here is another central cluster. See, this is another old cluster. This is the kind of cluster where people that are as old or me have been in that field. What do we have here? We have learning, artificial networks. So back then it was all artificial networks. You couldn't say neural networks. This is where a lot of people grew up that then later started the broader deep learning field. So you see a lot of, like, say, Jeff Hinton in that cluster. Artificial networks, models, adaptive systems. So these were mostly people who thought about brains and wanted to understand how do brains do things. And they were about neurons and spikes, and they were interested in the biology there. Let's look at one here, neural networks, a comprehensive foundation. There was one of the important textbooks there. Here we have 1982, John Hopkins paper, neural networks and physical systems with emergence collective computational abilities. He basically discovered that if we take neurons and we connect them with one another, we can store memory in the connections that we have between them. So those are the two old areas. Neither of those we will cover much. Like, we will not talk much about like actually spiking systems of neurons and so forth. So let's see what else we have. We have this whole cluster. And this is something that you will ultimately learn, which is reinforcement learning. All these papers are about reinforcement learning. They have their own language. They don't talk much with the vision guys. Sometimes they do, and that then leads to special papers that say combine a ConvNet with reinforcement learning. But here we have these papers. Let's look at a few classical papers. This is the book, the textbook on reinforcement learning. It's wonderful, it's beautiful. Sutton and Bartow, 2005. This is in a way where reinforcement learning really got its current shape. Now you can say, but today everything is deep Q learning. And yes, you will see deep Q learning, I promise, in this course. But what does it do relative to the original theories? Sutton and Bartow might have like, here's a function that estimates how much reward I will get if I follow this policy. What's the deep learning version of that? Here's a function that estimates how much we will get following this policy, and it's implemented as a deep neural network. But it's just a plug-in thing where you're like, okay, here's reinforcement learning algorithm. Let's put something in that makes something better. And now, of course, we do many things better. Like, we do better how our exploration strategy is better, and we do Monte Carlo tree search. Our position evaluation for, say, playing games like chess is better, and we use like ConvNets for that. There's all these things that we do better, but reinforcement learning is an old field. Let's look at like the very modern ones. Now, this is the new paper to Hassabis. Human level control deep reinforcement learning. That's one of the early papers from DeepMind. It's still much closer to what we do right now. And it gave rise to this whole like AlphaZero and so forth, Go, chess networks that we have these days. But they basically revisited this older literature and made it good, or like brought the deep learning improvements. So we have like this subcluster of old papers, that's reinforcement learning, and these new papers, which is kind of reinforcement learning to solve modern real world problems that are bigger, better, more complicated, play games like as good as humans ultimately do. And there you can look at the nearby things, like here, distributed prioritized experience replay. This is a trick to make these deep reinforcement learning systems a little better. Let's see, let's sample a few other, a brief survey. That's a review paper about what's going on in that area. Deep reinforcement learning from human preferences. Like, what if I want to do reinforcement learning for a robot and you tell me if that was good? But otherwise, it's the same reinforcement learning idea. It's just the human. And so on and so forth. And so this is one big cluster. And a good number of you will choose to be in that cluster. Then you want to understand the structure and gestalt of that cluster. What are all the different things that are happening in this space? Let's look at a few more clusters. What do we have here? Here, wireless learning architectures. Those are all papers that basically do machine learning with like real world systems. Think swarm robotics, think electrical power grids, think kind of all those things. In this area, no very, very highly cited papers, but lots of them. Here, let's look at a few of them to sample them here. Next generation access radio wireless networks. So these basically, that's like machine learning applied to radio networks. And these are all similar to one another because they basically bring machine learning / reinforcement learning outside of the domain where it is. You see, the cluster is somewhat close to reinforcement learning. They often use similar techniques. But what they have in common that they apply machine learning more to real world systems. So we're getting, so look, we have covered much of these areas that are just filled with old papers. So let's look at some of the newer papers. Let's zoom right into the middle. Now, you see one thing here, lots of very, very heavily cited papers. Let's zoom into this a little bit. What do we have here? Learning convolutional image recognition. This is where convnets happen in this space. Convnets are super heavily cited in large parts because they provide tools that everyone else is using. And the second one is they were the ones who popularized deep learning. So most sites in that field. Keep in mind that like everything that happened in that field was like a group of like a couple hundred people worldwide doing this obscure thing that was entirely useless, that people were just like, yeah, like funny. And then there were a few people who like had applications and startups doing something with it, but nothing much happened. These papers accumulated very, very few citations. And then deep learning happened with tens and hundreds of thousands of people on applications. So all of a sudden, the citations of all these papers went through the roof. That transition happened like over roughly the last 10 years, 8 years or something like that. Therefore, all those citations are new, and those papers that made that transition happen, the convnets, accumulated very large number of citations. Let's look at a few of them. This deep residual learning for image recognition, that's what's called ResNet, and we will talk about that. ResNet is basically you build a deep convolutional network, the gradients all get lost there, and therefore you have skip connection, or like you always have like, you basically only propagate the residuals, which is effectively a skip connection to the whole thing. So ResNet's huge influence on the field and was one of the early convnets. Here's AlexNet. Weirdly cited less, but this is a 2012 paper. This is the beginning of the deep learning field. This paper became incredibly successful. Why? Back then, people were using SIFT feature-based traditional machine learning, support vector machine-like things. And they were doing image competitions. And basically, Jeff Hinton with his team said, let's see if we can beat that. And they bet on neural networks. And AlexNet is a technical tour de force. They popularized a whole bunch of things that are still being used everywhere in vision networks, including they had ReLUs, and they had clever ways of initializing networks, and they were running on GPUs. In fact, it was kind of hilarious. They couldn't get everything onto one CPU, so they had 2 CPUs, that were split at the beginning and where they minimized the amount of computation between them, which weirdly gave rise to one GPU specializing on something and the other GPU specializing on other things. What else do we have here? Here we have very deep convolutional neural networks. That's what's it called? I don't remember the abbreviation, but in any case, it's one of the strategies. We will also talk about this when we come to state-of-the-art computer vision. It was kind of the next network that came after AlexNet. Else do we have here? ImageNet classification. Oh, hold on here. That's AlexNet. Hold on. Here's two versions of AlexNet. In any case, ResNet here. Gradient-based learning applied to document recognition. That's the oldest in this stack. What was going on there? This is basically Jan LeCun, considerably ahead of his time, doing convnets on postal servers. And I believe that it was commercially used for a long time. So if you want, AlexNet isn't like where deep learning started. It's just where deep learning became popular. People did the modern computer vision thing. Jan LeCun did it in '98. But if you want, like AlexNet basically added lots of bells and whistles to it to make it like work and scale and so forth. So this is that cluster. Let's look at another cluster. Here we have a cluster. Here we have NLP papers. Now, what you have? Learning recurrent speech using language recognition, translation, convolutional classification, and so forth. So let's look a little into this. Most cited papers, long short-term memory. This paper is the basis of virtually all of recurrent neural networks these days. So at least it's one of the most popular ones. It's a way of keeping memory. Why do you need memory when you deal with text data? Well, a word that we read in the past may be important right now. Say if I want to translate something, I need to keep information about that in my memory. LSTM is a major trick that we use to make that happen, and we will understand by the end of this course why it's so helpful. Other popular papers, sequence-to-sequence learning with neural networks. What's sequence-to-sequence learning? I want to do a translation. In come word after word after word, Conrad talking, and out should come another sequence, which is what Conrad just said in German. So we have a network, word coming in, word coming out. Potentially first it reads the sentence and then it puts out the words, or it like does it word by word in whichever order. Now, today we solve those problems with no longer with LSTMs, we solve them with transformers. But the techniques and the ideas behind it are still extremely similar between between recurrent neural networks and between transformers. Let's look at a few other papers here. Neural machine translation by learning to align and translate. One of the first Kyung-Yong Cho papers, I think, here. Efficient estimation of word representation in vector spaces. Basically, can I take a sentence, embed it in some high-dimensional space? And I should say, all these papers are popular papers. If you choose to stay in this area, you have a very good chance to choose one of these clusters. And in the end, you will know most papers in that cluster that are visualized here. Basically, everything that is visualized here is a classic. What else are the areas here? Here we have some specialized things. Adversarial learning that contains things like GANs, making, yeah. So this web page is 60years.vishub.ai. And how do I, and yeah, you can directly go there. It will be in the slide deck that I'm about to share. How did it come about? So I run this not-for-profit. And for the course that we were teaching, we wanted a visualization like that. And so a friend had introduced me to Strobolt. So I was like, hey, for this course, we'd really like this. And he said, yeah, we should do that. And he came in very, very late, just in time for the summer school. It was very cool. And then afterwards, he found that like It's really attractive for lots of people. I think it's super useful. I think for every topic that I ever learned in my life, I wish something like that should have existed. Like neuroscience, what are the main areas of neuroscience? No one knows. They have names, but how big are they? How popular are the papers? How did things change over time? No one knows. This kind of visualization really answers a lot of that stuff for me. Yeah. Here, generative adversarial nets. GANs. And we will do GANs. We have a whole week associated to it, which means GANs, if you haven't heard about it, are these systems that basically draw very realistic images. Like very, very realistic ones, realistic enough that you can do fake Amazon reviews with it. Let's see what we have here. Here we have image supervision. So this is basically a community that would like to solve that problem. I give you a photo, a bad photo, make it awesome. That means give me super resolution. I take a blurry image. Can I like fill it in with stuff that looks good? Can I deal with missing data? Can I correct things? Of course, it's relatively new. It's going to be used by Photoshop sooner or later, or probably already, and by all kinds of competitors to Photoshop, which is now an active paper exactly because these things are not possible. Like, can I take a scene and replace things with other things? Can I take a photograph of here and turn you all into dinosaurs? Or mad scientists? Okay, so this is another cluster. And I will be wrapping up very soon. Here we have another cluster, person re-identification. Lots of people are for ethically, maybe pragmatic, maybe less pragmatic reasons, are interested in, I take a photo of you. And then I have a camera at the airport and it tells me that you just showed up at the airport. Considerable sized field. We should talk about its ethical implications at some point of time. So I think we went through all the major clusters here. And you will see that kind of our course is organized a little around that. So we first, in the first couple of weeks, we learn the basics. You need to have that because if you don't have the theory, you can't really make progress in that area. And if you don't have that, and if you don't have the basic tools, you can't make progress. Now you need to, however you build your neural network, you need to initialize it, you need to optimize it, you need to regularize it, you need to kind of know where it is relative to all these others. And then in the following times, we will basically go through the three main application areas. We'll talk about recurrent neural networks and language processing and transformers. And it's going to be a sequence in a way where we basically cover this cluster. I'm sure transformers should be somewhere on it. I don't understand why it's not yet a big circle because transformers are really useful for most things. Hold on. No, first we will actually do convnets. Convnets are like this cluster here. And then we'll do envision. Like these are basically the applications of computer vision to all kinds of things. Here we have then natural language processing, and then we'll move on to reinforcement learning. So if you want, this general area will be stuff that we will have covered. This thing is very peculiar, this cluster. It's people having cool applications of ML to all kinds of specialized parts. So we will not be covering this cluster. And we will not be covering this cluster because a lot of the field has already moved on to do new things. Now, to be clear, there are lots of reasons to do support vector machines these days. It was a huge topic 15 years ago. It's still for many problems better and for many medical applications. Deep learning is not just not very useful, but there's three areas where it really shines. Deep learning is amazing at computer vision. Why? Because kind of, and then deep learning is really great at natural language processing, and it's really promising for reinforcement learning. Why is deep learning so good in those areas? These areas all have a lot of structure, and they all have a lot of structure that humans are not so good at describing. Like, tell me how you know that I'm Conrad, like, it's impossible. Tell me how you know that a patient is likely to get cancer. Well, you can say like, yeah, it's more likely because you smoke, and it's more likely because. But when it comes to the domain, so we can at least know something about it. Now we can say this thing should increase it. They're all relatively independent. In vision, inputs are very, very much not independent. Like, these all are points of my hand. They all depend on one another. It's really useful to use that information. And so they're all, deep learning is really good in those domains where we don't know how to produce the right features, and which we don't know in any of them. Like, what are the right features for chess? Like, yeah, there's like openness of position, but what does that even mean? Similar in Go. Like, it's hard to describe what's a good Go position versus not. Same thing with natural language processing. Like, why do you express a sentence in a certain way? I'm from Germany. I'm bad at expressing myself in English, and I had to learn the hard way how to say things the right way. And let me just tell you, for everyone who grew up in America, there's a lot of totally arbitrarily weird stuff in English language. And so in that sense, they're all domains in which deep learning can shine. And after this overview, I very much look forward to like go through all the rest of this area, to like all this outside, the upper outside of the system. And like, hopefully by the end of the course, you will have a good understanding of all those fields. You won't have the understanding of all the papers. No, we can't go that far. But you will have all that, which is the toolkit that you need to actually productively design deep learning systems that you can actually solve problems with. And I also want to say it's wonderful to see you in person. Thank you.